And we are live. Sorry that this has started about an hour and a half after I planned, but it took longer to put the slides together than I had imagined, and I didn't leave enough time for it. Nonetheless, we are ready to go. So, without further ado, let's get into it. So today we're going to cover some data structures and memory stuff. So we're going to look at pointers, arrays, how to loop through code, which makes our lives easier, how strings work and strings of text work in C, how functions can be declared and used in C, and at the end we're going to look at a bit of struct stuff. Now I apologize that there's no pre-prepared C for this, and it's mostly just slides, but should be fairly comprehensive. So we'll start off by with pointers, and all pointers are really ways to store memory addresses. Actually, before we start, I should probably note that if you are watching this live, there is a YouTube chat that you can watch, that you can contribute to. So if you have any questions, please pop them in there. And if you're watching this after the fact, feel free to if you're watching this after the fact, feel free to if you're watching this after the fact, feel free to tweet me questions, any questions that you have. Wow. Excuse me a moment. Be back shortly. It just seems that Google has messed up my slides. Just gotta take a few seconds to fix that. Which is mildly infuriating. Alright, back to where we started. Alright, so today we'll be looking at pointers, arrays, loops, strings, and functions and structure. If you have any questions, drop them into the live chat, which I'll be watching throughout the whole thing. If you have any questions, and you're watching this on YouTube or Open Learning after the live stream has occurred, please feel free to tweet me or email me any questions or hit me up on Open Learning. So we'll start off with pointers. Now, pointers are simply a way to store the address of a variable rather than a copy of the data that's used in it. And what this allows us to do is reference a variable elsewhere. Now, the uses of this may not be apparent at the moment, but the way they work is that we have a pointer of particular type, and the type of the pointer does matter, as it determines how we handle the data once we've, as we would say, dereferenced the pointer. So once we access the memory at where the pointer's to, the type of the pointer lets us know what sort of data is there, whether it's an integer, an unsigned integer, so on and so forth. And as you can see, you use the asterisk along with the normal type identifier to form the type, the pointer for that type. So as you can see in the example here, pointer data is an integer pointer. And instead of storing the data that's in actual data in there, we use the ampersand to get the address of that variable. And in order to dereference pointer data and get the variable and get the data from where it's pointing to, we use the asterisk. Because it's a pointer, when we use the asterisk before it and dereference it and we change its value, we're actually changing the value of the data that's stored in actual data. So as you look at the output down the bottom there, you'll see that actual data gets changed when we change the data that pointer is pointing to. The reason this is, as you can see, is so first of all, you can see from this diagram that pointers, as I mentioned last session, all have the same size. They're a full word long, and they point, and they simply store the address of the location of the data. This diagram's not entirely correct because the addresses are stored the wrong way round. However, for clarity, I've displayed it this way. But you can see that pointer data just holds the address, and actual data holds the number that we're looking for. So as I said, pointers have particular types, and you shouldn't go mixing them around. So say we have two variables of different types, one of an unsigned char and one of an int, and they're both containing numbers. And then we have a pointer to each of these variables. One's a pointer to an unsigned char, and one is a pointer to an integer. And there's a spelling mistake there. What we can do is dereference the pointers and then move the data between them. So we use asterisk to make the value in small data 56, because that's what the value in big data is. What we can't do is make the pointers themselves equal to each other, assign the value of one pointer to another, because they're pointers to different types of data. So that should be avoided. Next up, we have arrays, and arrays have some things in common with pointers, but we'll get to that in a moment. So here we have an array which is called numarray, and it's 10 elements long. And we say this array is going to have the elements 21, 22, 23, 24, 25, 26. And that's only 6 elements. What C will do is it will make the rest of the elements in that array that we haven't specified all equal to 0. Whenever we declare an array in C, we have to give it some indication of how long it is. So we either have to use those square brackets and put a number in there to give it an explicit length, or if you look down at small array, we can let it infer the length from the data that we give it. So in this, for small array, it's going to infers, because we've only given it 4 values, that it only needs to be an array for long. And in order to get a particular element of the array, much like with memory, how we refer to addresses in memory based on how far they are from the first address, we refer to elements in an array by how far they are from the first element. So the first element has an index of 0, the second element has an index of 1, the third has an index of 2, and so on and so forth. The reason that is if you look at the last two examples where we show the contents of the element, we can see that if we use numarray as if it's a normal pointer, and we dereference it with an asterisk, we get the first element. And then if we get num array and we add 3, we get the address of the third element. But if we look at size of, we find that the size of that array is 40. And that's because the type int uses 4 bytes to store every value. And size of tells us how much data is used in memory by that array. So likewise down the bottom, because it's storing 4 elements, it has a size of 16 bytes. So going back to where I have num array plus 3, you'd think, wouldn't that give you the address partway through the first element if it's going to only be plus 3 bytes? And the answer is no. When you're doing arithmetic with pointers and one type and one side of the arithmetic is a pointer, the other one gets multiplied by the size of that pointer. So because in the example there, num array is a pointer to an integer, when we add 3, we add 3 times the size of num array, and it does that automatically. So we get num array gets 12 bytes added to it, and we get to the fourth element. And as you can see in this case, because we've declared that as an array, it just takes up 10 consecutive blocks in memory for an int. You can also have multi-dimensional arrays, where it's just arrays within arrays. And you just specify that as shown there. You can have set the initial values using the array literals within each other, and you just specify how big the outer arrays are, and outer array is, and how big the inner arrays are. And every level of array, so if you have 2-dimensional arrays, the inner arrays all have to be the same length. If you have 3-dimensional arrays, the second level arrays have to be all the same length. The third level arrays all have to be the same length. And so when we get the size of multi-array, we get the size of the entire thing in memory. When we get the size of multi-array 0, which is the first array within it, we get the size of that single array. So to go along with arrays, I thought it might be useful to cover some loops. So loops let us run the exact same code over and over again until a condition is met. So the example we have here is we have a way of printing out every single item in that array. So we set our initial, we set index, which is what we're going to keep track of, and we set that to 0 with, so array 0 is going to be the first element in that array. And then we get the size of that array in elements. And what we do is that we increment, so we every time the loop goes, checks through itself, it checks that the current value of index is less than the number of items there is. As soon as index becomes large enough that it's equal to or greater than the number of items, that while loop stops looping. And so at the end of each loop, we will increment index by 1 after having printed the contents of that array element, as can be seen here. And so in this case, it will loop through that 9 times and then stop. And you can see we've used the incrementer there. Now, because it's a common pattern to loop by having some variable set to a particular initial value, then have it compared every loop to another value, and then at the end of each loop modify that variable by incrementing it or decrementing it or something else similar. We have the for loop, which takes those 3 actions and puts them in one line. So we have for, the first section before the first semicolon, tells us what the initial state of our loop is. So in this case, we're setting index to 0. And so that statement is executed before the loop starts. And then the second The second statement there between the two semicolons is the check that occurs every time the loop is run. And so before each loop is run, that test occurs, and if it's true, then the loop continues. And then the third section, the third statement there after the second semicolon is executed at the end of each loop and is used to increment the counter in this case before the test occurs. So as you can see, it takes the state of the loop and the way the loop works and compacts it all onto one line. So we can see how that loop is going to act all in one location there, which makes it a bit easier to read. And it has the same output as before. So it does the exact same thing, just a bit easier to read. Then we have strings. If you'll excuse me, I just need to fix up this slide. Strings are also arrays. As I mentioned before, all arrays, all strings are just arrays. All characters in ASCII can be represented by a particular number. So what we can do is we can create an array of character types, and using the single quotes, just assign a number for each character. Create an array with those numeric values for those characters, and then have the last value as a 0, as all strings in C have to end with 0. That's how we know to stop printing text, or looking at strings, or doing string comparisons. It's a very quick way of telling us that we've reached the end of a string. So we set up our array, we give it the letters for toast and an exclamation mark and a 0. And like before, we can iterate through this with for and get it to show us the value of each of these. We can even get it to print out the character. And at the end, it stops at 0. And here we've used size of, because it can tell us the size of the array in memory. And we've divided it by the size of the character to try and figure out the length of the string. We can also use %s and just the array itself, or the pointer to the start of the array, to actually print the context as the content as text, and printf will do that just fine. And in fact, we can use a string literal to create the exact same array. So we've swapped the array out for just a string, which is much easier to type, and you can see that it has the exact same effect. But what you'll commonly see is that strings aren't actually used as arrays of characters, but they're used as a pointer to an array of characters. And the way we calculate length using the size of string divided by size of the character type seems to break here, because now it's saying our array is 8 long. And the reason for this is that size of string here, when we were having it as using it as an array, is the size of each of the character types, is the size of the array in memory, because it's an array. But when we change it to a string, size of string now becomes the size of the pointer, which is going to be an entire word long. So if we look at this, you can see that when we declare string as a character array, it takes up 7 bytes and it contains the string itself. But when we declare string as a pointer to a character, it takes up 8 bytes. So our calculation for length stops working. And you can see it prints out the extra s here, and you can see that there's just an extra s in memory that it happened to catch, because it tried to print out 8 characters. Despite this, printf still works just fine. It stops because toast ends in a 0 and it stops displaying characters, or when it reaches that 0. So we'll overcome that in just a second. Another tool that we have in our toolbox is the function. Functions in C, you have to identify what type they're going to return. So for string length here, which is the function we've made, we have int, so it's returning an int size number. Its name is string length, and it has one argument, which is character array, which is a string. And so it's using the length calculation we were using before to try and calculate the length of that string. And it's an array there. We've declared it as an array. So we have main, and we pass in string 1, which is an array of characters, string 2, which is a pointer to an array of characters, so that's probably not going to work. And then we have a literal string as our third one, and we print each of these strings and then say how long they are. But in this case, it says that they're all 8 long. So even though, say, string 1 was an array of characters, and string length, the function, had an array of characters as its first argument, these all returned 8, which was the length of the pointer, not the length of the arrays, quite clearly. And the reason this is when you pass a string or any array into a function, they get passed as a pointer. And so all arrays get transformed into pointers. Even if you declare them as arrays like we have there, they all get treated as pointers when they enter a function as an argument. So to our function there, it looks like we're just looking for the length of the pointer that we have there, regardless of what string it's pointing to. So we can create a slightly smarter string length function, and we can use the fact that all strings end with a 0, a byte with equal to 0, in order to calculate that. So we have our length. We originally set it to 0, and we say, whilst the character in the array of string, because we can treat all pointers as arrays as well, it works both ways. So whilst the character at the location length in string is not equal to 0, just keep incrementing length. And so that will stop when the character at position equal to length is the 0 character. And that will be also, coincidentally, the number of characters that we've seen that aren't equal to 0, and we can return that. And you can see down the bottom that that works now. But this is a bit ugly, so we can also just clean up this function a bit. So what we've done in this slide here is, you can see at the top we have declared our functions. These function declarations just say what types each function returns, what the name is, and what all the arguments are, and nothing else. The reason we have to have those there is in order for the compiler to use those functions anywhere, it needs to know what types are involved and what order they occur in. But it doesn't need to know how the function works. So in fact, when you include .h files, like we have been for stdlib and stdio, they contain mostly just function declarations. They don't contain the code for the functions themselves, as the actual code for the functions is added in another way. But they contain those declarations so that when you type a function into use a function in your program, the compiler can check that you're using it correctly and that it gets called correctly. So we've got those declarations, and we've created a new function called testString. So instead of having that ugly long printf statement every time we wanted to see what a string looked like and how long it was, we have one function and we just hand that string to it once, and it creates the same output. And then we have the functions written below, and this just makes it easier to read through the entire thing. So we can see the main function, which gets called first, is what we're going to read first, and we can read down the program and see the functions that are used later on. That's just a note on clarity and style there, and it makes the program a lot easier to read. When you pass data into a function argument, the data is always copied into that argument. So say we have two functions here. We have our main function. We have a function called change, and it has an argument of an integer. So what we do here is we have in our main function, we have that integer, and that's the number 32. And then we print that number and we get down the bottom number is 32. And then we call the function change with the number 32. So that takes the number, and what change gets is a copy of the value 32. So when it prints that, and we say print the num that you got, the argument that you got, it prints 32, and then we change that to 64. It prints 64, but when our function stops running and it goes back to main, number in main is still 32 because it was only copied in. Now with arrays, because arrays work a lot like pointers, and because arrays are treated as pointers, what gets copied isn't the values that are stored in the array, but the address to it. And because of that, whenever we use arrays with function, we access the original data. So you can see that we print out the word happy, and then we call change. And because that's a pointer, when we change the first element of happy to an S, not only is it changed within change, but when we print it in the main function, that also gets printed as sappy. So that is something to be mindful when using arrays with functions. Then we have the call stack. So in order to keep track of what functions we were running and what functions we're currently running and what information is stored in which functions, the call stack is used to help the processor jump between areas where our program is running. So in this case, we're going to assume the call stack starts empty, and then we call main, and main is pushed onto the call stack. And then we print out, we set our array for word to being happy. We print it out and it says word is happy, and that calls printf, and that gets pushed on top of main. And then it gets popped off, and then we pop on change. So change is now run as a function on top of main. So change then calls printf, and printf gets pops on top of change, and that prints out text is happy. Then we change text to be an S. Printf gets popped on again and displays text is sappy. Then change ends, and that gets popped off. Printf gets popped on. Printf prints out word is sappy. And then main returns with exit success and ends, and it finishes there. So that's how we keep track of where the functions are. The way that works in memory is there is an actual area of memory referred to as the stack, which contains all of the information that's in each of the stack frames as shown on the right there. So when I say it's popped onto, there is actually a chunk of memory that is placed before the memory for... So when I say printf is popped onto the stack, the memory that has all of the data printf looks after and all of the information about what happens when printf finishes is placed before the memory for change, the information for change. And we call that block of memory that records all of the variables inside a function, where the instructions to return to once we finish a function are called, and the value we return, and whether the data for the function that we came from was the stack frame. And every function gets its own stack frame. So, for example, you might see the stack frame printf. This top one here might look like this. You'll have a pointer, which is the address, an address which points to F868, which is the middle of the stack frame, just before the return address for the frame for change. You'll see a return address, which is an address where there's instructions that the computer understands that it can jump to once this function is finished, and that'll be somewhere in the middle of the instructions for change. And then you'll see the arguments that were passed in to the function printf. So there's the format string that we passed in, and then there's the word that we were passing in as the first argument. So when we call printf, this all gets placed in memory before the frames for main and change, as can be seen here. And once printf finishes, all of that memory is unassigned, and if we call printf again, it just gets placed it just gets replaced with the whatever new function gets called in that area of memory. So once printf is done, we're left with change, and that has a pointer to the text we were modifying, the text that change was given, as well as the return address for that and the frame pointer for the main function, so that when change finishes running, we know where to jump in our code to finish off running main, and we know where the data for main was stored. And then once main finishes, the entire program ends. And down here in main, you can see main has the actual original array of where the data was stored. And lastly, here we have structs. Structs allow us to group data together in nice coherent globs so that we can pass it around. We can pass entire structs into functions and return entire structs from functions rather than turning just a single number. So in this case, we have a struct called color, and it's got 4 parts to it. It's got a red, green, blue, and an alpha, and they're all unsigned character types. And we can use those as unsigned character types. So when we have the struct itself, we can use a similar literal thing as we do for arrays to set the initial values. Then we have a printf statement, which just prints out the hex values for each of those in one long string. And it uses my color, which is the name of the variable for the struct, dot red, so that takes the red member of my color and uses the value for that. And that can be used like any other variable. We can assign values to it and so forth with that. When we have a pointer to a struct, we can use it like a normal pointer, so we can use asterisk and close brackets dot red in order to access red, but that gets a bit tedious having to dereference pointers like that. So we have another operator, which is the dash arrow, or stab as it's often referred to, which we can use after pointers to structs. So we have color pointer, which points to my color, as we've seen with pointers before, and we can use the stab operator to get to change the red value or access the red value, as can be seen there. And that's all structs really do. So they just let us group data together, and we can address them in the same way we can address just about any other variable, and mess around with them like any other variable type. In the next session, we'll go into how we can make these struct values slightly more useful, and how we can overcome the barrier that we've had so far, in that all of the data we have is stored on the stack. And that means that for any variable we have in a function, as soon as that function ends, the data in the variable stored in there gets disappears. So we can't pass data out of functions unless we copy the entirety of it. So in order to get around that, and in order to not be copying large globs of data around, we're going to look at dynamically allocating area in memory for use for storing data in the next session. Anyway, I hope this 40-minute rapid-fire sort of introductory C stuff has been helpful. I'll make sure that I put a link up in the description of this video, along with on Open Learning, with all of the examples and the slides that were used in this video. If you have any questions, please put them in the comments below. Cheers.